Everything you have ever seen is, in the strictest scientific sense, a fabrication. Not a lie born of deception, but a construction born of necessity. Right now, as your eyes move across whatever surface is presenting these words, you believe you are witnessing the world directly, as it truly is, in real time. You are not. You are experiencing a delayed, heavily edited, biologically rendered simulation, built from fragments of electromagnetic radiation that your nervous system has already decided are worth showing you. The raw universe, the actual physical phenomenon of light, has never once reached your conscious awareness. What reaches you instead is an interpretation, assembled by a 3-pound organ that evolved not to reveal truth, but to keep a fragile animal alive long enough to reproduce. This is not a philosophical parlor trick. It is a measurable, well-documented feature of neuroscience and physics, one that becomes stranger the more closely it is examined. Light, in its fundamental form, is one of the most exhaustively studied phenomena in the history of science. And yet the very organ you use to detect it, the human eye, is spectacularly restrictive in what it allows through. Consider the full electromagnetic spectrum, the entire range of radiation that exists in the universe. It stretches from gamma rays with wavelengths smaller than an atomic nucleus, through X-rays, ultraviolet light, and finally into the narrow sliver we call visible light, before continuing on through infrared, microwaves, and radio waves that can span the length of a football field or more. If you were to represent that entire spectrum as the distance between New York and Los Angeles, the portion your eyes can actually detect would be smaller than the width of a single postage stamp. Everything else, the overwhelming majority of the electromagnetic universe, simply does not exist for you, perceptually speaking. It passes through and around your body constantly, indifferent to your inability to register it. This narrow window was not designed with truth in mind. It was shaped by roughly 540 million years of evolutionary pressure, beginning with simple light-sensitive patches on ancient marine organisms and gradually refining into the camera-like eyes that primates, including humans, eventually inherited. The visible spectrum your eyes detect, roughly 400 to 700 nanometers in wavelength, happens to correspond almost exactly to the range of light that passes most efficiently through Earth's atmosphere and is most abundantly emitted by our Sun. This is not a coincidence about the universe revealing itself to you. It is a coincidence about survival. Organisms that could detect the wavelengths most abundant in their environment gained an advantage in finding food, avoiding predators, and navigating terrain. Vision, from its earliest evolutionary origins, was never optimized for accuracy. It was optimized for usefulness, even within that narrow sliver of detectable light. What you consciously experience is not a live broadcast. It is closer to a heavily produced highlight reel, delivered after a measurable delay. Neuroscientists have calculated that the brain requires somewhere in the range of 1/10 of a second, sometimes longer depending on the complexity of the scene, to process visual information before it enters conscious awareness. That means you are, quite literally, always perceiving the past. The image you believe you are seeing right now already happened. Your brain received the raw sensory data, processed it, compared it against memory and prediction, filled in the gaps, and only then presented you with a finished product labeled as now. For most everyday purposes, this lag is irrelevant, small enough to be functionally invisible, but it reveals something profound about the nature of perception itself. Your conscious experience of sight is not a transparent window onto reality. It is a construction, assembled after the fact, packaged to feel immediate, even though it never truly is. This delay becomes especially significant when you consider fast-moving events. Studies involving professional athletes, particularly baseball players, attempting to hit a pitch traveling at high speed, have shown that the ball is often partially or entirely out of a batter's direct visual awareness by the time the brain finishes processing its trajectory. The athlete's brain compensates by predicting where the ball will be, essentially guessing ahead of the incoming sensory data rather than reacting to it in true real time. In other words, elite athletic performance depends not on seeing reality accurately, but on the brain's capacity to forecast reality slightly ahead of the delayed information it actually receives. Perception, in this light, functions less like a camera and more like a weather forecasting system, constantly predicting what is about to happen based on incomplete and outdated data. If you want to understand why this matters on a deeper level, it helps to think about what light actually is at a physical level, stripped of any biological interpretation. Light is electromagnetic radiation, a self-propagating disturbance of electric and magnetic fields that carries energy through space, including the vacuum of space itself. At exactly 299,792,458 meters per second, it requires no medium to travel through, a fact that took centuries of scientific struggle to establish, and it behaves, depending on how it is measured, as either a wave or a stream of discrete particles called photons. This dual nature alone should make you suspicious of your intuitive understanding of light, because nothing in ordinary human experience behaves the way photons do. But before we can appreciate just how strange the true nature of light is, we first need to understand what happens biologically the instant a photon strikes your eye, because that process, more than anything else, explains why your perception of the world is fundamentally an interpretation rather than a direct observation. Around the first quarter of this exploration, it becomes worth pausing to genuinely sit with an uncomfortable question. If your entire visual experience is a delayed, filtered, and reconstructed approximation, what else about your perceived reality might be operating on the same principle? Sound, touch, even your sense of your own body in space are all similarly processed, similarly delayed, similarly incomplete. The implications reach far beyond optics and into the very architecture of consciousness itself. If this idea intrigues you, staying with this exploration through to its conclusion will reveal just how far the rabbit hole extends, from the smallest interactions between photons and proteins, all the way to the philosophical question of whether any conscious being could ever perceive reality as it truly is. The journey of a single photon into your conscious awareness begins with an act of destruction. A photon of visible light having potentially traveled for 8 minutes and 20 seconds from the surface of the sun, or in the case of starlight, for thousands or even millions of years across interstellar space, finally reaches the surface of your eye. It passes through the cornea, the transparent outer layer that provides most of the eye's focusing power, then through the pupil, an aperture whose size is continuously adjusted by the iris to regulate how much light enters. It continues through the lens, which fine-tunes the focus, and finally strikes the retina, a thin layer of neural tissue lining the back of the eyeball that is, in developmental terms, actually an extension of the brain itself rather than a separate organ. Within the retina lie two primary types of photoreceptor cells, rods, which number around 120 million per eye and are exquisitely sensitive to low light but cannot distinguish color, and cones, numbering around 6 million per eye, which require brighter light but allow for color vision through 3 subtypes tuned roughly to short, medium, and long wavelengths. When a photon strikes one of these photoreceptors, it does not bounce around indefinitely or get seen in any direct sense. Instead, it is absorbed by a light-sensitive molecule called retinol, a derivative of vitamin A, which is bound to a protein called opsin. The absorption of that photon causes retinal to change shape almost instantaneously in a process called photos, converting from a bent molecular configuration called into a straightened form called ultrans retinal. This single molecular shape change triggers an extraordinary biochemical cascade known as phototransduction. The shape change in retinal activates the opsin protein, which in turn activates a G protein called transducin, which activates an enzyme called phosphodiesterase, which then breaks down a molecule called cyclic guanosine monophosphate. This breakdown closes ion channels in the photoreceptor's membrane, changing the cell's electrical charge, which ultimately alters the release of neurotransmitters at the base of the cell. In simpler terms, a single photon, an almost unimaginably small packet of energy, is capable of triggering a chain reaction so effectively amplified that a fully dark-adapted human eye can, under controlled laboratory conditions, detect the arrival of a single photon at the retina. This sensitivity is close to the theoretical physical limit of what is possible, a remarkable achievement of biological engineering refined over hundreds of millions of years. But here is the critical point. None of this process constitutes seeing light in any objective sense. What is actually happening is a chemical translation. Photons, physical particles carrying specific quantities of energy determined by their wavelength, are being converted into electrical signals, patterns of neurotransmitter release and neuronal firing that carry no inherent resemblance to the light that caused them. A photon of a wavelength around 700 nanometers and a photon of a wavelength around 450 nanometers are physically nothing alike in the way. For example, a large object and a small object are alike but different in size. They differ in a fundamental physical property, their frequency of oscillation. Yet your brain represents this difference not with any accurate physical description, but with the qualitative sensations you know as red and blue. There is nothing inherently red about long wavelength light. Redness is not a property that exists in the photon itself. It is a label, a symbol, generated entirely within your nervous system, arbitrarily but consistently assigned to a particular pattern of neural activity. This distinction matters enormously, and it connects to one of the most persistent debates in the philosophy of mind, sometimes called the qualia problem. Even if two people both look at the same object and both correctly identify it as red, there is no way to confirm that their internal, subjective experience of redness is identical. One person's experience might, in some sense that can never be externally verified, resemble what the other person would call blue, while both have simply learned to attach the word red to whatever internal sensation arises from long wavelength light. Color, in other words, is not a property of the external world waiting to be discovered. It is a construction that exists only within a nervous system capable of generating conscious experience, built from meaningless electrochemical signals that the brain has learned, through evolutionary and developmental processes, to organize into a stable, useful, but entirely subjective palette. The scale of data reduction involved in this process is staggering. It has been estimated that the human retina, across both eyes, receives on the order of 10 million bits of information per second from incoming light. However, the optic nerve, the bundle of roughly 1 million axons carrying visual information from each eye to the brain, has a maximum transmission capacity far lower than that, generally estimated at around 6 million bits per second combined, and the amount of that information which ultimately reaches conscious awareness is smaller still, often estimated at somewhere between 10 and 100 bits per second by the time it becomes something you consciously notice and could report on. This means that somewhere between 90 and 99.9% of the raw information striking your retina at any given moment is discarded before it ever reaches your conscious mind. This is not a flaw in the system. It is an essential feature, without which conscious experience as we know it would be impossible. A nervous system attempting to consciously process the full, unfiltered stream of raw photonic information would be instantly and catastrophically overwhelmed. Evolution solved this problem not by increasing processing capacity indefinitely, which would require impractical amounts of energy and neural tissue, but by developing sophisticated filtering, compression, and prediction systems that discard the vast majority of incoming data, while preserving only what is likely to be behaviorally relevant. Movement, contrast, edges, faces, and sudden changes are prioritized. Static, unchanging, predictable information is often filtered out almost entirely. A phenomenon you can observe directly. Stare at a fixed point in your peripheral vision for long enough, and unchanging details there tend to fade from conscious awareness. Even though the photons are still striking your retina exactly as before, consider also the structure of your own retina, which contains a curious design flaw that further complicates the notion of unmediated vision. The photoreceptor cells are counterintuitively oriented backward, with the light-sensitive segments facing away from incoming light and toward the back of the eye, meaning light must pass through several layers of neurons and blood vessels before reaching the receptors themselves. This arrangement also creates a blind spot, a small region on the retina where the optic nerve exits the eye and where no photoreceptors exist at all. You have two of these blind spots, one in each eye, and yet you almost never notice them, because your brain actively fills in the missing information using surrounding visual context, essentially fabricating a seamless image over a region where no actual data exists. This filling-in process is not a passive gap left empty. It is an active construction, a genuine hallucination generated to preserve the illusion of a complete, continuous visual field. Taken together, these facts paint a picture of vision that is radically different from the naive assumption most people carry throughout their lives. You do not see light. You experience a heavily compressed, extensively edited, actively constructed representation built from a vanishingly small fraction of the electromagnetic spectrum, processed through biochemical reactions that convert physical energy into arbitrary neural symbols, filtered to discard the overwhelming majority of incoming information, and delivered to conscious awareness only after a measurable delay, during which extensive prediction and fabrication have already occurred. And this is merely the biological half of the story. To understand just how strange the true nature of light is, and how radically it defies the simple, solid, particle-like intuition most people carry, we need to travel back through the history of physics itself, to a series of experiments and theoretical breakthroughs that revealed light to be one of the most genuinely paradoxical phenomena in the entire universe. The construction of visual experience does not end once electrical signals leave the retina. It merely begins there. Those signals travel along the optic nerve to a small relay station deep within the brain called the lateral geniculate nucleus, part of the thalamus, before being routed to the primary visual cortex, a region at the very back of the brain known as V, which represents only the first of many stages in an extraordinarily elaborate processing hierarchy. From V1, visual information fans out along at least two major pathways, often described as the dorsal stream and the ventral stream. The dorsal stream, sometimes summarized as the Ware pathway, travels toward the parietal lobe and specializes in processing spatial location, motion, and the coordination of vision with physical action, such as reaching for an object. The ventral stream, sometimes summarized as the What pathway, travels toward the temporal lobe and specializes in object recognition, including highly specialized regions such as the fusiform face area, a small patch of cortex that appears to be particularly dedicated to recognizing human faces, so specialized that damage to this specific region can produce a striking condition called prosopagnosia, or face blindness, in which a person retains completely normal vision for objects, colors, and scenes, yet loses the ability to recognize even highly familiar faces, sometimes including their own reflection in a mirror. This division of labor reveals something crucial. Your brain does not process a single unified image the way a camera captures a single photograph. It processes dozens of distinct visual features, including color, motion, depth, edges, orientation, and object identity in parallel, across many specialized and anatomically distinct brain regions, and then somehow binds these separately processed streams back together into the single, seamless, unified conscious experience you take entirely for granted. Exactly how the brain accomplishes this binding, reassembling dozens of separately processed features into one coherent, unified percept without any obvious central location where all this information converges, remains one of the significant unsolved puzzles in neuroscience, sometimes referred to as the binding problem. There is no single location in the brain, no theater screen or central viewing chamber, where a complete image is finally assembled and displayed for some inner observer to watch. The unified visual scene you experience is itself an emergent construction, arising from the coordinated activity of dozens of specialized regions working in concert, none of which individually possesses anything resembling a complete picture. This architecture also explains certain rare and specific neurological deficits that further demonstrate the modular, constructed nature of vision, a condition called achinotopsia, resulting from damage to a specific motion processing region known as V5 or mount, leaves affected individuals with entirely normal static vision, capable of clearly seeing colors, shapes, and objects, but with a profound and specific inability to perceive motion. Patients with this rare condition have described the disorienting experience of watching liquid being poured into a cup as a series of discrete, frozen still images rather than a continuous flowing motion, as though the world were being presented to them as a slideshow rather than a smooth video. Cases like achinotopsia and prosopagnosia demonstrate with striking clarity that vision is not one single capacity that either works or fails as a whole. It is a carefully coordinated assembly of many separate, specialized subsystems, any one of which can fail independently while leaving the others fully intact, further reinforcing the idea that ordinary, seamless visual experience is an achievement of extraordinary neural coordination, not a simple, passive reception of external light. This layered architecture of construction, filtering, prediction, and reassembly bears a striking resemblance to an idea proposed roughly 2,400 years ago, long before any of this neuroscience existed, by the Greek philosopher Plato in his famous allegory of the cave, described in his work known as the Republic. Plato imagined prisoners chained since birth inside a cave, facing a blank wall, able to see only shadows cast upon that wall by objects and figures passing in front of a fire behind them. Having never seen anything else, these prisoners mistake the flickering shadows for the entirety of reality itself, entirely unaware that a richer, more complete world exists beyond their limited perceptual access. Plato intended this allegory primarily as a metaphor for philosophical enlightenment and the difference between opinion and true knowledge, but read through the lens of modern neuroscience and physics, it takes on an almost eerily literal resonance. Human beings, quite genuinely, perceive only a narrow, shadow-like projection, filtered through a narrow range of the electromagnetic spectrum, processed and reconstructed by specialized neural machinery, while a vastly larger and stranger underlying reality, encompassing the full electromagnetic spectrum and the deeper quantum nature of light itself, remains permanently outside direct perceptual access, much as the true forms outside Plato's cave remained inaccessible to prisoners who had only ever known shadows. This is not to suggest that Plato somehow anticipated quantum mechanics or retinal biochemistry through pure philosophical insight. Rather, it suggests that the fundamental structure of the problem, the gap between appearance and underlying reality, has been recognized in various forms across nearly the entire history of human intellectual inquiry, from ancient philosophy through medieval optics to modern physics and neuroscience. Each era has approached the same essential puzzle using the tools available to it, and each has arrived through very different methods at strikingly similar conclusions: that what is directly perceived is not identical to what actually exists, and that bridging this gap requires indirect methods, whether philosophical reasoning, careful experimentation, or sophisticated instrumentation, rather than simple, unaided observation. Modern physics has extended this humbling lesson even further, revealing that electromagnetic radiation, the very phenomenon this exploration has focused on, is not even the only category of information traveling through the universe that remains completely inaccessible to unaided human perception. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves, ripples in the fabric of space-time itself, predicted by Albert Einstein's general theory of relativity a full century earlier, generated in this instance by the collision of two black holes over 1 billion light-years away. Gravitational waves are not electromagnetic radiation at all. They are literal distortions in the geometry of space and time, and they pass through the Earth and through your body, constantly, though almost always at magnitudes so infinite, small that no conceivable biological sense organ could ever hope to detect them without extraordinarily sensitive, laser-based instrumentation capable of measuring distortions thousands of times smaller than the width of a proton. The detection of gravitational waves represents an entirely separate category of invisible information about the universe, distinct from anything on the electromagnetic spectrum, and it underscores just how much of physical reality exists entirely beyond the reach, not just of human vision specifically, but of human sensory perception as a whole in any form, where electromagnetic radiation at least permits indirect detection and translation into visible false color imagery. As with infrared and X-ray astronomy, gravitational waves required humanity to develop an entirely new category of scientific instrument, one with no direct biological analog whatsoever, simply to confirm that this category of physical phenomenon existed at all. The universe, it turns out, communicates through channels your body was never built to receive, using not just narrow slices of the electromagnetic spectrum, but entirely separate physical phenomena altogether, of which gravitational waves may be only one example among others not yet discovered. Perhaps the most accessible, immediately demonstrable evidence for the constructed nature of vision comes not from laboratory equipment or rare neurological disorders, but from a category of everyday phenomena nearly everyone has directly encountered: optical illusions. Far from being mere entertaining party tricks, well-designed optical illusions function as precise experimental probes, revealing the specific assumptions, shortcuts, and predictive strategies the brain relies upon to construct visual experience, exposing that hidden machinery by presenting it, with situations where its normal assumptions produce a demonstrably incorrect result. Consider the checker shadow illusion, developed by the vision scientist Edward Adelson in 1995. In this illusion, two squares on a checkerboard pattern, one located within an apparently shadowed region and one located outside it, are printed using the exact same shade of gray, identical down to the pixel. And yet, to nearly every human observer, the square within the shadow appears distinctly lighter than the square outside the shadow, a difference so persistent and convincing that even after being shown irrefutable proof, using a simple digital tool that isolates the two squares side by side, confirming their identical coloration, most viewers continue to perceive the illusion just as strongly as before. This occurs because the visual system does not report raw, unadjusted brightness values. It actively compensates for what it interprets as shadow, applying an automatic, unconscious correction based on assumptions about how shadows typically affect apparent brightness, a process known as lightness constancy, which evolved because it is generally useful, allowing you to correctly recognize that a white shirt remains white whether viewed in bright sunlight or in shade, rather than perceiving the shirt as literally changing color every time the lighting conditions shift. A closely related and famous example is the internet phenomenon, commonly referred to simply as the dress, a photograph that went viral in February of 2015, showing a striped dress that different viewers, looking at the identical photograph, confidently and often heatedly perceived as either blue and black or white and gold, with no middle ground and often genuine disbelief that other people could possibly be seeing the same image differently. Researchers who studied this phenomenon determined that the disagreement stemmed from differing, automatic, unconscious assumptions individual visual systems were making about the lighting conditions under which the photograph was taken. Viewers who unconsciously assumed the dress was photographed under blue-tinted lighting, common in overcast daylight, tended to perceptually discount the blue tones in the image, effectively subtracting them out during processing, resulting in a perceived white and gold dress. Viewers who instead unconsciously assumed the photograph was taken under warmer, artificial indoor lighting perceived the image differently, resulting in blue and black. In both cases, viewers were looking at the exact same array of pixels, the exact same objective photonic information, yet their respective visual systems, making different automatic assumptions about ambiguous contextual lighting cues, constructed genuinely different conscious color experiences from identical raw input. This single photograph, more effectively than perhaps any laboratory experiment before it, demonstrated to millions of ordinary people in real time and on a massive scale that color is not a fixed property residing in an image or an object, but a conclusion actively constructed by an individual nervous system based on assumptions that can genuinely differ from one observer to another, even when the external stimulus is held perfectly constant. Color constancy, the broader perceptual mechanism underlying both of these illusions, operates continuously throughout ordinary daily experience, almost entirely without conscious awareness. Your visual system is constantly making automatic, unconscious inferences about the color and intensity of ambient light illuminating a scene, and then effectively subtracting or compensating for that inferred lighting in order to estimate the true, stable, underlying color of objects, a computation of impressive sophistication. Given that no measuring instrument is available to directly determine the actual color composition of the ambient light source, the visual system must essentially solve a challenging inverse problem, working backward from the combined signal, which mixes both the actual reflective properties of an object and the color of the light illuminating it, to estimate the object's underlying reflective properties alone. discarding the lighting component as unwanted variability. This computation is generally performed with remarkable accuracy and near total unconscious effort, which is precisely why illusions capable of tricking this system, by presenting deliberately ambiguous or misleading contextual lighting cues, feel so surprising and counterintuitive when they succeed. Motion illusions offer a similarly revealing window into the brain's predictive machinery. Consider certain rotating snake illusions, static, two-dimensional images composed of carefully arranged patterns of light and dark shapes, which the vast majority of viewers perceive as continuously rotating or shimmering, despite the image containing no actual movement whatsoever, no changing pixels, and no genuine physical motion of any kind. These illusions exploit specific neural mechanisms within motion-detecting regions of the visual cortex, mechanisms normally responsible for detecting the small, rapid eye movements called microsaccades that occur constantly, even during apparently steady fixation, along with specific patterns of contrast and luminance that inadvertently trigger the same neural motion detection circuitry that would normally respond to genuine physical movement. The resulting illusory perception of motion is not a failure of vision. It is, in a strange sense, the motion detection system correctly and faithfully reporting a genuine internal neural signal, a signal that happens, in this specific and carefully engineered case, to be triggered by something other than actual external motion. Ambiguous figures provide yet another compelling category of illusion. Images constructed such that they can be perceptually interpreted into entirely distinct, mutually exclusive ways, with the viewer's conscious experience spontaneously flipping back and forth between the two interpretations, sometimes every few seconds, even though the underlying physical image on the page or screen never changes at all. The famous Rubens vase illusion, which can be perceived either as a symmetrical vase or as two facial profiles facing each other, and the equally famous duck-rabbit illusion, which can be perceived either as a duck or as a rabbit, depending on which features the visual system emphasizes. Both demonstrate that the same identical pattern of raw photonic input can produce genuinely different conscious percepts, determined not by any change in the external stimulus, but purely by which interpretive model the brain happens to be applying at that particular moment. Researchers studying these bestowable perception phenomena have used them as valuable tools for isolating and studying the neural correlates of consciousness itself, since they offer a rare situation in which the external physical stimulus can be held perfectly, experimentally constant, while the resulting conscious experience changes, allowing scientists to more precisely identify which specific patterns of neural activity correspond directly to subjective conscious perception, as opposed to the earlier stages of unconscious visual processing that remain constant throughout. The perceptual flip. Taken together, this entire category of illusions, from shadow-based lightness, constancy, to color constancy exemplified by the viral dress photograph, to motion illusions exploiting microsacco detection circuitry, two bestowable, ambiguous figures revealing the brain's active interpretive choices, provide some of the most direct, personally verifiable evidence available that ordinary visual experience is not a passive, transparent window onto external reality. It is an active, ongoing process of inference, prediction, assumption, and construction, one that generally serves you remarkably well in navigating the ordinary physical world, precisely because it has been refined over an immense span of evolutionary time to extract useful, generally reliable conclusions from ambiguous and incomplete raw sensory data. But the very same predictive, assumption-laden machinery that makes vision so useful in everyday life is also precisely what guarantees that vision can never constitute unmediated, direct access to the true underlying physical nature of light, an underlying physical reality that, as the deeper journey through quantum mechanics and biology already revealed, may not even possess a single, fixed, definite character prior to the very act of being observed. Long before Newton ever split white light through a prism, human beings had already been debating the fundamental nature of vision for well over 2,000 years. And the earliest theories reveal just how counterintuitive the true mechanics of sight actually are, even to careful, intelligent observers working without modern instrumentation. The ancient Greek philosopher, writing in the 5th century before the Common Era, proposed what became known as the extramission theory of vision, the idea that the eyes themselves emit some form of visual fire or ray, which travels outward, strikes objects in the world, and thereby allows those objects to be perceived. This theory, strange as it sounds today, was taken seriously for centuries, partly because it offered an intuitive explanation for why closing your eyes seems to actively block vision, as though a beam were being switched off, and partly because it aligned with a broader philosophical framework in which the eye was considered an active, projecting organ rather than a passive receiver. The philosopher Euclid, better known for his foundational work in geometry, also adopted a version of extramission theory around 300 years before the Common Era, using it to mathematically describe the geometric properties of visual rays, effectively founding the field of geometric optics even while operating under a fundamentally incorrect model of how vision actually worked. It was not until the work of the Arab scholar Ibn al-Haytham, known in the Western world as Alhazen, working in the early 11th century, that a fundamentally correct model of vision as an intromission process, light entering the eye from external objects rather than being emitted by it, was rigorously established through careful experimentation. Alhazen's 7-volume work, known as the Book of Optics, used controlled experiments involving a device resembling a pinhole camera, along with careful anatomical study of the eye, to demonstrate conclusively that light travels from luminous or illuminated objects into the eye, rather than the reverse. His work represents one of the earliest and most rigorous applications of the experimental scientific method in history, predating the so-called scientific revolution in Europe by several centuries, and it laid essential groundwork that later European scientists, including Johannes Kepler and eventually Newton himself, would build upon. This centuries-long historical struggle to correctly understand even the basic directionality of light entering the eye underscores an important point. The true nature of vision is not something obvious or intuitively accessible, even to the most brilliant thinkers observing it carefully. If it took humanity roughly 1,500 years to correctly determine that light travels into the eye rather than emerging from it, it should come as no surprise that the deeper quantum nature of that light and the true extent of the electromagnetic spectrum remained completely unknown until the tools of modern physics became available in the 19th and 20th centuries. Human intuition about vision has consistently lagged behind physical reality, correcting itself only gradually through careful experimentation, mathematical modeling, and technological innovation, each step revealing that the previous understanding was incomplete or fundamentally mistaken. This historical pattern of humbling correction becomes even more apparent when human vision is compared against the sensory capabilities of other species, a comparison that reveals just how arbitrary and narrow the human perceptual window truly is, even among other biological organisms occupying the same physical planet. Consider the mantis shrimp, a marine crustacean possessing what is widely regarded as the most complex visual system known among animals, with up to 16 distinct types of photoreceptor cells. Compared to the three cone types found in typical human trichromatic vision, mantis shrimp can detect ultraviolet light, infrared light, and even polarized light, a property of light waves related to the orientation of their oscillation, which is completely invisible to unaided human perception. Some species of mantis shrimp are believed to perceive circularly polarized light, a capability found almost nowhere else in the animal kingdom, and one that scientists still do not fully understand in terms of what practical advantage it confers. Honeybees, meanwhile, perceive ultraviolet light, wavelengths shorter than 400 nanometers that lie entirely beyond the range visible to human eyes. Many flowers have evolved ultraviolet patterns, invisible to humans but strikingly visible to bees, that function as nectar guides, essentially runway markings directing pollinators toward the reproductive structures of the plant. A flower that appears to human eyes as a uniform, unmarked yellow petal may, to a bee's visual system, display a vivid, high-contrast bullseye pattern, radically different information encoded in the very same physical object, rendered completely inaccessible to one species while being essential, functional information to another. This example alone should be sufficient to dismantle any lingering assumption that human color perception represents some objective, complete, or privileged view of reality. It is simply one particular filtering strategy, evolved to suit the particular ecological needs of a particular species, no more fundamentally correct than the 16-channel system of the mantis shrimp, or the ultraviolet inclusive trichromatic system of the honeybee. Birds offer another instructive comparison. Many bird species possess tetrachromatic vision, meaning for distinct types of color-sensitive cone cells, rather than the three found in typical human vision, often including sensitivity to ultraviolet wavelengths. This grants many birds the ability to perceive plumage, patterns on other birds of their own species that are completely invisible to human observers, patterns that may play crucial roles in mate selection and species recognition. Some bird species that appear, to human eyes, to display no meaningful difference between males and females, are in fact strongly sexually dimorphic under ultraviolet inclusive avian vision, displaying dramatic differences that remained completely undetected by human ornithologists until ultraviolet sensitive cameras were developed to reveal them. In contrast, dogs and most other mammals possess only dichromatic vision, based on two cone types rather than three, resulting in a visual world with substantially reduced color discrimination compared to typical human trichromatic vision. Though often compensated by superior sensitivity in low light and a wider field of peripheral view, even within the human species itself, meaningful variation exists. A small percentage of women, due to a genetic phenomenon involving mosaic expression of cone photopigment genes on the X chromosome, possess 4 functional types of cone cells rather than the standard 3, a condition sometimes referred to as tetrachromacy, potentially granting them the ability to distinguish subtle color differences that remain completely indistinguishable to the vast majority of trichromatic humans. Researchers who have studied confirmed human tetrachromats have found that these individuals can reliably discriminate between colors that appear visually identical to standard trichromatic observers, suggesting that even the specific, seemingly fixed and universal category of normal human color vision actually spans a range of genuinely different perceptual experiences, rather than representing a single, uniform, objective standard shared identically by every person. This comparative biological survey drives home a point that connects directly back to the interface theory of perception discussed earlier. There is no privileged, complete, or objectively correct way to perceive light. Every visual system across the animal kingdom, from the 16-channel mantis shrimp to the ultraviolet sensing honeybee to the tetrachromatic bird to the standard trichromatic human, represents merely one particular filtering strategy among countless possible strategies, shaped by the specific evolutionary pressures and ecological needs of that particular lineage. None of these systems accesses the true, complete, underlying electromagnetic reality. Each accesses a different narrow slice, filtered and interpreted according to different biological machinery, optimized for different survival tasks. The idea that human vision represents some default, standard, or authoritative window onto physical reality is revealed, through this comparative lens, to be nothing more than an anthropocentric assumption, unsupported by any deeper physical or biological principle. In the year 1704, Isaac Newton published a work titled Optics, in which he laid out his theory that light was composed of tiny, discrete particles, which he called corpuscles, traveling in straight lines and obeying mechanical laws similar to those governing the motion of physical objects. Newton's reputation, already immense following the publication of his work on gravitation and motion, lent enormous authority to the corpuscular theory of light, and for over a century, it remained the dominant scientific framework for understanding what light fundamentally was. Newton's model explained reflection reasonably well, treating light particles as bouncing off surfaces the way a ball bounces off a wall, and it offered a satisfying, intuitive, mechanical picture that fit comfortably within the broader Newtonian worldview of a clockwork universe governed by predictable physical laws. But Newton's corpuscular theory struggled to explain certain phenomena, particularly the behavior of light when passed through narrow openings or thin films, where patterns of alternating bright and dark bands appeared that seemed inconsistent with simple particles traveling in straight lines. A contemporary of Newton, the Dutch physicist Christian Huygens, proposed an alternative, that light was not a stream of particles at all, but a wave, propagating through a medium in a manner similar to ripples spreading across the surface of water. Huygens's wave theory offered better explanations for phenomena like diffraction, but it faced a significant conceptual problem. If light was a wave, what medium was it waving through? Sound waves require air or some other material to propagate. Water waves require water. Scientists of the era assumed light waves must similarly require some substance to travel through, and they invented a hypothetical medium called the luminiferous ether, an invisible, weightless, frictionless substance believed to permeate all of space, providing the medium through which light waves could ripple. For over a century, the corpuscular and wave theories competed for scientific dominance, with Newton's immense authority generally keeping the particle theory ascendant despite mounting evidence favoring waves. The turning point came in 1801, when the English polymath Thomas Young conducted what has since become one of the most famous experiments in the history of physics, the double-slit experiment. Young directed light through two closely spaced narrow slits and observed the pattern it produced on a screen behind them. If light behaved as discrete particles, one would expect two bright bands on the screen, corresponding to the two slits. Instead, Young observed a complex pattern of multiple alternating bright and dark bands, a phenomenon known as an interference pattern, which occurs when two waves overlap, sometimes reinforcing each other and sometimes cancelling each other out, exactly as would happen if two sets of ripples on a pond's surface intersected. This result provided compelling evidence that light behaved as a wave, and it began to shift scientific consensus decisively away from Newton's particle theory. The wave theory of light received further, powerful support in the 1860s, when the Scottish physicist James Clerk Maxwell developed a set of equations describing electricity and magnetism as two aspects of a single unified phenomenon, electromagnetism. Maxwell's equations predicted the existence of self-propagating electromagnetic waves traveling at a speed that, when calculated from known electrical and magnetic constants, matched almost exactly with the experimentally measured speed of light. This was a profound and unifying discovery. It suggested that light itself was simply one manifestation of electromagnetic radiation, occupying a narrow band within a much larger spectrum that also included, as later experiments confirmed, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays and gamma rays, all fundamentally the same phenomenon, differing only in wavelength and frequency. By the end of the 19th century, the wave theory of light appeared triumphant, elegantly unified with the broader framework of classical electromagnetism, and the particle theory of Newton seemed relegated permanently to the status of a historical curiosity. Then, in 1905, a young patent clerk in Switzerland named Albert Einstein published a paper that would append this seemingly settled picture entirely. Einstein was attempting to explain a puzzling phenomenon known as the photoelectric effect, in which light striking certain metal surfaces caused electrons to be ejected from the material. Classical wave theory predicted that the energy of these ejected electrons should depend on the intensity, or brightness, of the incoming light. But experiments showed something different and deeply strange. The energy of the ejected electrons depended not on the intensity of the light, but on its frequency, meaning its color. Dim light of a high frequency, such as violet or ultraviolet, could eject electrons with more energy than intensely bright light of a lower frequency, such as red. This made no sense under a purely wave-based model of light. Einstein's radical proposal was that light, despite the overwhelming evidence for its wave nature, also behaved as discrete packets of energy, which he called light quanta, and which later came to be known as photons. The energy of each individual photon, Einstein proposed, was directly proportional to its frequency, following a relationship first identified by the German physicist Max Planck a few years earlier in his work on blackbody radiation. This elegantly explained the photoelectric effect. A single photon of sufficiently high frequency carried enough energy in one discrete packet to eject an electron, regardless of how many total photons, meaning how bright the overall light, were present. Einstein's explanation of the photoelectric effect, published in the same extraordinary year as his papers on special relativity and Brownian motion, would later earn him the Nobel Prize in Physics in 1921, notably not for his more famous work on relativity, but specifically for this insight into the particle-like nature of light. This left physics with an apparently contradictory situation. Young's double-slit experiment and Maxwell's equations provided compelling evidence that light behaved as a wave. Einstein's explanation of the photoelectric effect provided equally compelling evidence that light behaved as discrete particles. Both could not seemingly be true simultaneously under classical physical intuition, and yet both were experimentally verified beyond reasonable doubt. This apparent paradox, now known as wave-particle duality, became one of the founding puzzles of the emerging field of quantum mechanics. Throughout the early 20th century, the situation grew even stranger as physicists refined the double-slit experiment further. When researchers sent individual photons through the double-slit apparatus, one at a time, with long enough intervals between each photon that only one could possibly be in the apparatus at once, the interference pattern still gradually emerged on the detection screen after many individual photons had been fired. This meant that each individual photon, alone, with no other photon present to interfere with, was somehow behaving as though it were interfering with itself, as if it were simultaneously passing through both slits at once and interfering with its own trajectory. This behavior is described mathematically by what physicists call the wave function, a mathematical object that does not describe a photon's definite position or path, but rather a probability distribution describing the likelihood of finding the photon at any given location. Should a measurement be made, perhaps the strangest element of this entire picture is what happens when physicists attempt to determine, through some measuring device, which of the two slits a photon actually passed through. The moment any measurement is made to extract this which path information, the interference pattern disappears entirely, and the photons begin behaving as simple particles, producing two distinct bands on the screen rather than the complex interference pattern. This phenomenon, sometimes described as the collapse of the wave function upon measurement, suggests that a photon exists prior to being measured, in a strange indeterminate state that does not correspond to any classical notion of a particle having a single definite location and trajectory. It is neither simply a wave nor simply a particle in the way those terms are ordinarily understood. It is something else entirely, a genuinely quantum phenomenon for which human intuition, evolved to navigate the macroscopic world of objects and forces at ordinary scales, provides no adequate mental model. This is, perhaps, the single most important reason your eyes cannot show you light as it truly exists. The human visual system, however sophisticated its biochemistry, was never built to detect quantum superposition or wave function probability distributions. It was built to detect the practical, statistically averaged outcome of enormous numbers of photon interactions, translated into stable, useful categories like brightness and color. Even if you could somehow directly perceive individual photons one at a time, what you would be perceiving is not some hidden, deeper truth about light waiting to be unveiled. It would be a probabilistic quantum event that does not resolve into a definite state until it interacts with a detector, whether that detector is a piece of laboratory equipment or the retinal proteins inside your own eye. In a very real sense, your retina does not passively receive pre-existing light. It participates in determining what that light becomes, collapsing quantum possibility into a specific, singular biochemical event. Every single time a photon is absorbed, this raises a genuinely unsettling philosophical question. Was the photon red or blue, or any particular wavelength before it struck your eye? Or did it exist as an indeterminate probability distribution until the act of detection itself forced it into a definite outcome? Quantum mechanics does not provide a fully settled answer to this question even today. Over a full century after these puzzles first emerged, different interpretations of quantum mechanics, including the Copenhagen interpretation, the many worlds interpretation, and pilot wave theories, offer competing philosophical frameworks for understanding what is actually happening at this fundamental level, and physicists continue to debate which, if any, provides the correct picture of underlying reality. What remains beyond dispute, however, is that light, examined closely enough, refuses to conform to any simple, intuitive picture, whether that picture involves solid particles or continuous waves. It exists in a genuinely strange quantum regime that human perception was never designed to directly access, only to translate imperfectly and probabilistically into the stable visual experience you rely on every waking moment. If evolution had been optimizing for accuracy, for a truthful, high-fidelity representation of physical reality, one might expect natural selection to have gradually pushed perceptual systems toward ever more faithful reproductions of the actual universe. But a growing body of theoretical work in cognitive science suggests the opposite may be true. The cognitive scientist Donald Hoffman, building on decades of research into perception and evolutionary game theory, has proposed what he calls the interface theory of perception. In simulations comparing organisms that perceive reality accurately against organisms that perceive only a simplified, fitness-relevant interface, Hoffman's models consistently show that perceptual accuracy is driven to extinction by perceptual usefulness. In other words, organisms that evolved to see the world as it truly is were consistently outcompeted in these theoretical simulations by organisms that evolved to see a simplified set of practical cues correlated with survival and reproduction, even when those cues bore little resemblance to underlying physical truth. Hoffman uses an analogy that has become widely cited. Your perceptual experience functions something like the desktop interface on a computer. When you see a blue rectangular icon on your screen representing a document file, that icon does not resemble the actual electronic structure of the file in any way. The file itself, at the level of physical reality, consists of patterns of magnetized regions on a hard drive or transistor states in solid-state memory, arrangements of binary information stored as electrical charges. None of that resembles a blue rectangle in any conceivable sense. The rectangle is a simplified, useful symbol, deliberately designed to hide the underlying complexity and present only what is functionally relevant to a user who needs to open, move, or delete the file without needing to understand transistor-level physics. Hoffman's provocative claim is that conscious perception functions analogously. Colors, shapes, and objects as you experience them are not literal descriptions of physical reality. They are functional icons, evolved symbols that hide an underlying reality far too complex, and in the case of quantum mechanics, far too counterintuitive, for a biological nervous system to represent directly while still functioning effectively enough to survive and reproduce. This idea, while still debated within cognitive science and philosophy of mind, resonates strongly with what we already understand about the biology and physics of vision. Evolution did not select for eyes capable of perceiving the true quantum nature of electromagnetic radiation, because such perception would have offered no survival advantage over a simpler system, and would likely have imposed an enormous, unnecessary computational cost. What natural selection favored instead were systems capable of rapidly and efficiently extracting behaviorally relevant information. The location of a predator, the ripeness of fruit, the presence of another member of one's species, the edge of a cliff, from an overwhelming stream of electromagnetic noise. The resulting visual system is spectacularly good at this narrow, practical task, and correspondingly poor, or more accurately, entirely disconnected from any task involving the direct perception of underlying physical truth. This raises the question of what happens when the brain's usual construction process breaks down, when the machinery generating your visual interface malfunctions in ways that reveal the underlying mechanics of perception. Neurology offers several striking case studies that illuminate just how actively fabricated ordinary vision really is. Consider a rare and deeply counterintuitive condition known as Anton-Babinski syndrome, in which a person becomes cortically blind, typically due to damage in the occipital lobe, the region of the brain primarily responsible for processing visual information, yet remains completely unaware of their own blindness. Patients with this condition will confidently describe objects and scenes in a room that they cannot actually perceive, confabulating detailed visual experiences that have no correspondence to their actual surroundings, and will often become confused or frustrated when they bump into furniture they insisted they could see. This condition demonstrates, in a stark and unsettling way, that the brain's sense of seeing and the actual reception of visual data are two entirely separable processes. The conscious experience of vision can persist, fabricated wholesale by the brain, even when the underlying sensory apparatus has completely failed. A related but distinct phenomenon is blind sight. observed in patients who have suffered damage to the primary visual cortex and report complete subjective blindness in the affected region of their visual field. And yet, when forced to guess the location or movement of an object presented in that blind region, perform significantly better than chance, sometimes with remarkable accuracy. These patients have no conscious visual experience of the stimuli whatsoever, and genuinely believe they are guessing randomly. Yet some part of their nervous system is clearly still processing visual information and using it to guide behavior. This suggests that visual processing and visual consciousness are not the same thing, and that substantial visual information processing can occur entirely outside of and disconnected from subjective conscious awareness. Your conscious visual experience, in other words, is not simply what the eyes detect. It is a specific, curated, conscious summary generated by particular neural pathways, layered atop a much larger and largely unconscious processing system. Perhaps even more revealing is what happens during sensory deprivation, when the brain is deprived of its normal stream of visual input altogether. In a controlled setting known as a Ganzfeld experiment, participants are exposed to a completely uniform, unstructured visual field, often achieved by covering the eyes with halved ping-pong balls illuminated by soft, diffuse, unpatterned light. Within a relatively short period, often just minutes, a significant proportion of participants begin to report vivid hallucinations, shapes, colors, textures, and sometimes complex scenes that have no correspondence to any actual external stimulus. Deprived of meaningful patterned input to interpret, the visual system does not simply go dark. Instead, it appears to actively generate content, drawing on internal expectations, memories, and predictive models to fill the resulting perceptual void. This phenomenon offers a striking clue about the fundamental nature of visual consciousness. It may be less like a passive window receiving information from outside, and more like an active hallucination that is, under normal circumstances, tightly and continuously constrained by incoming sensory data, but which reveals its constructive, generative nature the moment that external constraint is removed. This idea has gained substantial traction within a modern theoretical framework in cognitive neuroscience known as predictive processing, or predictive coding. Under this framework, the brain does not primarily function as a passive receiver of sensory information, building up a picture of the world from the bottom up, starting with raw data and gradually assembling it into perception. Instead, the brain is understood to be constantly generating predictions, top-down models of what it expects to encounter, and comparing those predictions against incoming sensory signals. What you consciously experience, according to this framework, is primarily the brain's best predictive model, continuously updated and corrected by incoming sensory data, but fundamentally generated from the inside out rather than assembled from the outside in. The cognitive scientist Anil Seth has popularized a memorable description of this process, describing perception as a form of controlled hallucination, a hallucination that is normally reined in and corrected by real sensory information, but which is, at its core, a generative, predictive, actively constructed process rather than a direct readout of external reality. Under this view, the difference between ordinary perception and a full-blown hallucination is not that one involves construction and the other does not. Both involve construction. The difference lies in how tightly that construction is being constrained and corrected by actual incoming sensory evidence. In ordinary waking perception, sensory data continuously anchors and corrects the brain's predictive model, keeping the hallucination tethered closely enough to physical reality that it remains functionally accurate and reliable for everyday purposes. In conditions like sensory deprivation, certain neurological disorders, or altered states induced by extreme fatigue, or certain substances. That anchoring weakens, and the brain's generative, predictive machinery becomes more visible, producing perceptual experiences that diverge significantly from the actual external environment. Even ordinary dreaming, during which the brain generates rich, immersive, often visually detailed experiences with no external light entering the eyes at all, offers further evidence that the visual system's fundamental capability is generative construction, not passive reception. Perception was never a mirror. It has always been closer to an elaborate, continuously updated, and normally well-constrained work of internal fiction. This framing also helps explain why direct perception of true, raw electromagnetic reality would likely be not just biologically impractical, but genuinely impossible for any nervous system resembling ours. The raw quantum behavior of light, existing as probability distributions, rather than definite states prior to measurement, spanning wavelengths from picometers to kilometers, arriving at rates of trillions of photons per second under ordinary illumination, would represent an amount and a type of information that no biological nervous system, constrained by the energy budgets and processing speeds available to living tissue, could possibly represent directly in real time. Some filtering, compression, and interpretation is not merely a limitation to be overcome with better biology. It is a mathematical and physical necessity for any finite system attempting to make sense of an effectively infinite, informational environment. Even a hypothetical alien organism with vastly superior sensory organs would still, by necessity, be perceiving some filtered, compressed, and interpreted version of reality, rather than reality unmet. The question is not whether perception involves construction. Every conceivable form of perception must. The question is only how narrow, how filtered, and how differently shaped that construction happens to be. There exists a further neurological phenomenon that reinforces just how flexible and constructed color perception truly is. Synesthesia, a condition in which stimulation of one sensory or cognitive pathway involuntarily triggers experiences in another. Some individuals with a specific form of synesthesia, called grapheme color synesthesia, CONSISTENTLY, perceive particular letters or numbers as inherently possessing specific colors. Seeing the numeral 5, for instance, as intrinsically red, or the letter A as intrinsically blue, despite the fact that these symbols are printed in ordinary black ink and carry no actual chromatic information whatsoever. This is not a metaphorical description or a learned association in the ordinary sense. Brain imaging studies have shown that synesthetic color experiences activate the same visual color processing regions of the brain, particularly in areas sometimes referred to as V4, that are activated when a person views actual physical color, despite there being no corresponding physical light stimulus of that color present at all. In these individuals, the brain's construction of color has become cross-wired with its processing of abstract symbols, generating a fully genuine, involuntary color experience from an input that carries no chromatic information in the external, physical world whatsoever. Synesthesia offers a particularly clear demonstration of a principle that runs throughout this entire exploration. Subjective visual experience, including the experience of color, is generated internally by neural activity. And while that internal generation is normally triggered and shaped by external photonic stimuli, the underlying generative machinery can, under certain neurological conditions, be triggered by entirely different non-visual input and still produce a fully convincing conscious experience of color. This further undermines any simple notion that color is a property residing in the external world, waiting passively to be detected. Color is manufactured by the brain, typically in response to specific wavelengths of light striking the retina. But the manufacturing process itself, it turns out, can be decoupled from that typical trigger entirely, while still producing what feels, from the inside, like an entirely ordinary and vivid visual experience. A related and more universally experienced phenomenon is the which most people have encountered directly. Stare at a brightly colored image for an extended period, then look away toward a blank white surface, and a ghostly, color-inverted version of the original image will appear to hover in your visual field for several seconds, even though no actual light corresponding to that image is present at that later moment. This occurs because the photoreceptor cells responsible for detecting the original color become temporarily fatigued from prolonged, intense stimulation, altering the relative balance of signals sent to the brain once the eyes move to a new, neutral surface. The brain, receiving this skewed signal, constructs a color experience that does not correspond to any actual external light source at all in that moment, once again illustrating that what you perceive as color is generated internally, based on a complex interplay of retinal signal processing rather than a direct one-to-one readout of external photonic reality. Dark adaptation offers yet another window into how dramatically your visual experience is shaped by internal, biological processes rather than a stable external reality. When you move from a brightly lit environment into darkness, your visual sensitivity does not adjust instantly. Cone cells, responsible for color vision and functioning best in bright light, adapt relatively quickly, within several minutes, but rod cells, responsible for low-light vision, require a much longer adaptation period, often 20 to 30 minutes, to reach their maximum sensitivity, as light-sensitive rhodopsin molecules gradually regenerate within the rod photoreceptors. This is why your eyes seem to slowly get used to darkness over time, a process during which your perception of the exact same physical environment changes dramatically, revealing details and shapes that were completely invisible when you first entered the dark space. Even though the actual physical light levels present in that environment have not changed at all during the adaptation period, the world did not become more visible. Your internal biochemistry simply completed a slow chemical recalibration, once again demonstrating that what you perceive depends as much on the internal state of your nervous system as it does on the external physical stimulus itself. Returning to the deeper quantum strangeness of light itself, the physicist John Archibald Wheeler in the 1970s proposed a conceptually radical extension of the double-slit experiment known as the delayed choice experiment. In Wheeler's thought experiment, later realized in actual laboratory conditions using sophisticated equipment, the decision of whether to measure which path a photon took through a double-slit apparatus is delayed until after the photon has already, in some sense, passed through the slits, but before it reaches the final detection screen. Remarkably, experiments have confirmed that the outcome, whether the photon behaves as a wave producing an interference pattern, or as a particle producing a simple two-band pattern, appears to depend on this later measurement choice, even though that choice is made after the photon has already traversed the slit apparatus. This produces the deeply counterintuitive implication that a measurement made later in time appears to influence, or at minimum correlate with, the behavior a photon exhibited earlier in its journey, challenging naive, everyday intuitions about the fixed, sequential flow of cause preceding effect. A closely related experiment, known as the quantum eraser, deepens this puzzle even further. In these experiments, researchers first mark photons with which path information that would ordinarily destroy the interference pattern, causing the photons to behave as simple particles. But if that which path information is later erased, made permanently unrecoverable through a subsequent measurement process, Before the final detection occurs, the interference pattern reappears, as though the earlier marking had never happened at all. These experiments do not actually involve any literal time travel or genuine retrocausal signaling, and physicists are careful to note that no information can be transmitted backward through time in any way that violates causality or allows faster-than-light communication. But they do reveal, with remarkable experimental rigor, that the classical, intuitive notion of a photon following a single, definite path through space and time, a path that could, in principle, be known and photographed at every stage of its journey, simply does not correspond to how quantum systems actually behave. The photon's story is not written until the full experimental context, including choices made at later points, is complete. These experiments matter enormously for understanding why your eyes cannot show you true light, because they demonstrate that even a hypothetical observer equipped with perfect, unlimited sensory equipment, capable of detecting every single photon with complete precision, would still not be able to access some fixed, definite, pre-existing property of what the light really was prior to measurement. The very act of measurement, of detection, whether performed by a photomultiplier tube in a physics laboratory or by a rod cell in your retina, is not a passive readout of a pre-existing fact. It is an active physical interaction that participates in determining the outcome. This is perhaps the deepest and strangest twist in this entire exploration. It is not simply that your biology filters and interprets a pre-existing, definite, objective light signal. At the most fundamental quantum level, there may be no fully definite, pre-existing signal to filter in the first place, until some physical detection event, your own retina included, forces the underlying quantum possibility into a concrete, measurable outcome. If the boundaries of perception are set by biology rather than by physical reality itself, an intriguing question follows naturally. Can those biological boundaries be deliberately extended through technology, allowing a human nervous system to gain access to portions of the electromagnetic spectrum or other physical phenomena that evolution never equipped it to detect? Remarkably, several real-world experiments suggest the answer may be yes, at least to a limited but genuinely functional degree, and the results offer some of the most compelling evidence yet that perception is fundamentally a matter of information processing rather than a fixed, hardwired biological ceiling. Consider the case of Neil Harbison, a colorblind artist born with a rare condition called achromatopsia, meaning he perceives the world only in shades of gray, with no color discrimination whatsoever. In 2004, Harbison began wearing a device, which he and collaborators called an eyeborg, consisting of a small camera mounted above his head connected to a chip that converts detected color frequencies into corresponding sound frequencies, transmitted through bone conduction directly to his skull. Over time, Harbison reported that he no longer consciously translated these sounds into a color label the way a person using a color naming chart might. Instead, he described directly experiencing the sounds themselves as color, developing what he describes as a genuine sensory perception distinct from ordinary hearing that allows him to perceive color despite his biological colorblindness. Harbison later extended the device to detect wavelengths entirely outside the human visible spectrum altogether, including infrared and ultraviolet light, converting these normally invisible wavelengths into their own distinct sound frequencies, meaning he can now, in a very real, functional sense, perceive electromagnetic information that unaugmented human vision, even fully typical, non-colorblind human vision, is completely incapable of detecting. This case, however unusual, is far from an isolated curiosity. It fits within a broader and increasingly well-studied field known as sensory substitution, in which information normally associated with one sensory modality is converted into a different modality that a person's nervous system can still access. The neuroscientist Paul Bachwayeta pioneered early research in this area beginning in the 1960s, developing devices that converted camera images into patterns of vibration delivered to the skin of blind participants' backs or tongues. With sufficient training and practice, several blind participants reported that they eventually stopped consciously perceiving the vibrations as mere tactile sensations on their skin, and instead began to experience something resembling genuine spatial perception of the objects and environment the camera was capturing, essentially learning to see using patterns of touch processed by brain regions that had never received visual input in that person's lifetime. This remarkable neural flexibility, known as cross-modal plasticity, demonstrates that the specific sensory channel through which information enters the nervous system is, to a meaningful degree, less important than the fact that the information enters the nervous system at all. In some structured, learnable pattern, the brain, it turns out, is far more concerned with extracting useful structured information than with which particular biological channel that information originally arrived through. A particularly striking demonstration of this principle comes from studies of blind individuals who have taught themselves human echolocation, using self-generated tongue clicks and listening carefully to the returning echoes to navigate their environment, identify the presence, size, and even material composition of nearby objects, and in some remarkable documented cases, ride bicycles safely through unfamiliar environments using this technique alone. Brain imaging studies of expert blind echolocators have found that processing these echo signals activates regions of the brain normally associated with visual processing, rather than purely auditory regions, suggesting that these individuals have effectively repurposed their visual cortex, deprived of its usual input from the eyes, to process spatial information arriving instead through sound. This finding reinforces the idea discussed earlier in the context of the interface theory of perception, that the brain's various perceptual regions, at some fundamental level, general-purpose information processing systems, capable of being trained to extract spatial, structural, and object-related information from whatever data stream is made reliably available to them, rather than being permanently and exclusively hardwired to process only light specifically. Researchers working in this field, including scientists such as David Eagleman, have gone further still, developing experimental sensory substitution devices designed not merely to restore lost function, but to grant entirely new forms of perception that no human has ever naturally possessed. One such device, a vibrotactile vest developed in Eagleman's laboratory, converts various forms of real-time data, including sound for deaf users, or in some experimental configurations, live financial market data or real-time infrared thermal information, into complex patterns of vibration delivered across the torso. Early research participants using these devices for extended training periods have reported a similar transition from consciously interpreting the vibration patterns as abstract signals toward a more direct, intuitive, almost effortless sense of perceiving the underlying information itself. If further research continues to validate and extend these preliminary findings, it would suggest that the specific, narrow perceptual boundaries evolution originally provided to Homo sapiens may not represent an immovable, permanent ceiling on human experience, but rather a flexible, extendable starting point, one that technology may increasingly allow individuals to expand beyond, granting forms of perceptual access to portions of physical reality, whether ultraviolet light, infrared radiation, or entirely non-electromagnetic data streams. that unaided biological evolution never provided. This possibility carries a genuinely profound implication. If sensory substitution research continues to mature, future generations might have access to forms of perceptual experience entirely unavailable to anyone living today. Not through some radical alteration of the fundamental laws of physics, but simply through better technological methods of routing existing physical information into a nervous system already remarkably capable of learning to interpret novel data streams as genuine felt experience. The narrow window of ordinary human vision, in other words, may turn out to be not a fixed biological law, but merely the default configuration that evolutionary pressure happened to settle upon across hundreds of millions of years. One among countless other possible configurations that a sufficiently adaptable nervous system, given the right training and the right technological interface, might eventually be capable of accessing. None of this technology, it is important to emphasize, grants access to some final, complete, or truly objective view of physical reality either. Even a hypothetical future human equipped with augmented ultraviolet vision, infrared perception, and some form of gravitational wave sensory substitution would still be experiencing a translated, filtered, technologically mediated version of underlying reality, subject to the same fundamental constraints. The finite processing capacity of a biologically or technologically augmented nervous system, the necessity of converting physical phenomena into some form of internally interpretable signal, and, at the deepest quantum level, the apparent necessity of measurement itself in determining definite physical outcomes from underlying probabilistic potential. Expanding the boundaries of perception, however remarkable an achievement, does not eliminate the fundamental gap between the perceiver and the thing perceived. It merely pushes that boundary outward, revealing more of what lies beyond. While the deepest layer of physical reality, the raw, unmediated, observer-independent nature of light and matter themselves, likely remains permanently beyond the reach of any conceivable act of direct perception, biological or technological. If human biology forever bars direct access to the true electromagnetic spectrum, science has nonetheless developed remarkable technological workarounds, instruments that extend perception, albeit indirectly, into realms your eyes were never built to detect. These technologies do not grant humans a magical new sense. They translate invisible radiation into visible representations, converting data your eyes cannot register into false color images your visual system can interpret, offering a kind of borrowed glimpse into portions of reality that remain permanently inaccessible to unaided biological sight. Consider infrared radiation, electromagnetic waves with wavelengths longer than visible red light, emitted by virtually all objects with any temperature above absolute zero, meaning essentially everything in the observable universe. Thermal imaging cameras detect this radiation and convert it into visible light images, typically rendering warmer regions in reds, oranges, and yellows, and cooler regions in blues and purples. Firefighters use these devices to locate people through smoke. Wildlife researchers use them to track nocturnal animals, and astronomers use far more sensitive infrared instruments, such as the James Webb Space Telescope, launched in December of 2021, to peer through clouds of interstellar dust that would completely obscure any view in ordinary visible light, revealing newly forming stars and some of the earliest, most distant galaxies ever observed, whose light has been stretched into infrared wavelengths by the expansion of the universe itself over more than 13 billion years. At the opposite end of the spectrum lie X-rays and gamma rays, extraordinarily high energy, short wavelength forms of electromagnetic radiation associated with some of the most violent and energetic events in the universe. exploding stars, matter spiraling into black holes, and the superheated gas within galaxy clusters. Earth's atmosphere fortunately blocks most of this radiation from reaching the surface, which is essential for life, but also means that X-ray and gamma-ray astronomy requires instruments positioned above the atmosphere, such as the Chandra X-ray Observatory, launched in 1999, which has captured detailed images of supernova remnants, black hole accretion disks, and hot gas threading the space between galaxies, none of which would ever be visible to a human eye, no matter how powerful. Positioned at the same location, radio astronomy occupies the other extreme of the spectrum, detecting electromagnetic waves with wavelengths ranging from roughly 1 millimeter to hundreds of kilometers. Because individual radio telescopes would need to be impractically large to achieve sharp resolution at these long wavelengths, astronomers developed a technique called interferometry, linking together multiple smaller radio dishes, sometimes separated by distances spanning entire continents, or, in the case of the Event Horizon Telescope, effectively the diameter of the Earth itself, and combining their data to synthesize the resolving power of a single enormous instrument. This technique produced, in April of 2019, the first ever direct image of a black hole's event horizon, located at the center of the galaxy Messier 87, roughly 55 million light-years from Earth, rendered as a glowing ring of superheated matter surrounding a region of absolute darkness. No human eye and no conceivable evolutionary adaptation could ever have produced that image directly. It required translating radio wavelength data, invisible to biological vision, painstakingly collected over years and processed through enormous computational effort, into a false color, visual representation that a human brain could finally interpret. These technologies illustrate something important. The boundary of human perception is not the boundary of physical reality, and it never has been. There is far more occupying the space around you and passing directly through your body at this very moment than your biology permits you to register. Radio waves from distant galaxies, cosmic microwave background radiation left over from the early universe roughly 13.8 billion years ago, X-rays from medical equipment, ultraviolet radiation from the sun capable of causing skin damage you cannot perceive until well after the exposure has occurred, and the faint infrared glow radiating from your own body and every object around you, are all present, all physically real, and all entirely invisible to unaided human sight. The room you are in right now is, in a very real sense, awash in forms of light your biology has no capacity to detect. The silence and apparent darkness surrounding wavelengths outside the visible spectrum is not an absence of activity. It is an absence of your ability to perceive that activity. This naturally leads toward a deeper philosophical question that has occupied thinkers for centuries, long before modern physics or neuroscience existed to frame it in scientific terms. The 18th century philosopher Immanuel Kant drew a foundational distinction between what he called the phenomenon, the world as it appears to a perceiving mind, shaped and structured by that mind's particular faculties of perception and cognition, and the noumenon, the thing as it exists in itself, entirely independent of any observer, which Kant argued could never be directly known or accessed by any conscious being. Kant arrived at this conclusion through pure philosophical reasoning, centuries before scientists could explain phototransduction cascades or quantum wave function collapse, and yet his conclusion aligns remarkably well with what modern physics and neuroscience have independently discovered, that the raw, unmediated nature of physical reality, including the true nature of light itself, may be permanently and fundamentally inaccessible to any observer whose perception must necessarily be filtered through a physical detection and interpretation system. Whether that system is a biological eye and brain, or a scientific instrument and its associated data processing, this does not mean that science is powerless, or that objective knowledge about the universe is impossible. Quite the opposite. The entire history of physics represents a remarkable, centuries-long project of using indirect measurement, mathematical modeling, and careful experimentation to infer the properties of a reality that can never be directly, subjectively experienced. Physicists cannot see an electron, cannot directly perceive a quantum wave function, and cannot personally witness the curvature of space-time around a massive object. And yet, through careful, repeatable measurement and rigorous mathematical formalism, they have built extraordinarily accurate and predictive models of phenomena that lie entirely outside the boundaries of direct human sensory experience. Science, in this light, can be understood as a systematic method for building reliable knowledge about a reality that consciousness itself can never directly touch. A way of triangulating truth indirectly through instruments and mathematics, precisely because direct perceptual access is permanently unavailable. What remains genuinely unresolved and continues to be an active area of research and debate among physicists, neuroscientists, and philosophers of mind is the deeper question of consciousness itself. Why does any of this biochemical and electrical processing give rise to subjective experience at all? Why does the activation of certain neurons in response to a 550 nanometer wavelength photon produce the felt, subjective quality of seeing green, rather than simply producing behavior without any accompanying inner experience? This question, sometimes called the hard problem of consciousness, remains one of the most significant unsolved puzzles in modern science. No current theory, however sophisticated its account of neural processing, phototransduction, or predictive coding, fully explains why physical processes should be accompanied by subjective, felt experience at all, rather than occurring, as far as anyone can currently determine from the physics alone, entirely in the dark. Researchers continue to make progress on adjacent questions. Advances in optogenetics, a technique allowing scientists to control specific neurons using light, are helping map precisely which neural circuits correspond to particular aspects of visual experience. Brain-computer interfaces are beginning to explore whether visual information might someday be transmitted directly into the nervous system, bypassing the eyes entirely for patients with certain forms of blindness, hinting at a future where the boundary between biological and artificial perception grows increasingly blurred. Quantum physicists continue probing the strange behavior of photons at ever smaller scales, testing the boundaries of wave-particle duality with increasingly sophisticated experiments, some of which have delayed the moment of measurement itself in ways that seem to retroactively determine whether a photon behaved as a wave or a particle earlier in its journey. A phenomenon known as delayed choice experiments, first proposed conceptually by the physicist John Archibald Wheeler and later confirmed experimentally, deepening rather than resolving the mystery of what light actually is prior to being observed. What can be said with confidence, drawn from more than 3 centuries of careful science, stretching from Newton's earliest optical experiments to the most advanced quantum measurements of the present day, is this: light is real, light is measurable, and light behaves according to consistent, well-understood physical laws. But light, as it truly exists, independent of any observer, has never been, and perhaps can never be, directly experienced by any conscious being constrained by a physical nervous system. What you call seeing is an achievement, an extraordinary biological and neurological accomplishment refined over hundreds of millions of years of evolution. But it is an achievement of translation and interpretation, not of direct, unmediated access to physical truth. The next time you look around the room you are in, consider, just for a moment, everything present in that space that you are constitutionally unable to perceive. The infrared warmth radiating from every surface, the faint trace of cosmic radiation left over from the birth of the universe passing silently through the walls. The radio waves carrying broadcasts and wireless signals crisscrossing the air around you undetected. You are, and have always been, standing inside a far larger and stranger reality than your eyes were ever built to reveal, perceiving not the universe itself, but a narrow, ancient, remarkably effective, and permanently incomplete translation of it.